Hi again, everyone. Chris Tisdell here again. Thanks for tuning in. In this presentation, we are going to learn or revise how to solve linear systems. And by linear systems, I mean special kinds of simultaneous equations. So we'll talk about the need, we'll talk about the process, and we'll do a few examples. And I'm going to use Geogebra to give you some good visualization of what's going on. So let me share my screen with you and we can start. So welcome to Intro to Linear Systems. So where are we going? Well, we are going to discover or revise, depending on how much you know about these things, so-called linear systems. And linear systems are just a fancy way of describing certain types of simultaneous equations. Now, linear systems are absolutely amazing because they have so many applications. For example, in economics, you have supply and demand dynamics, engineering, control models. You may have also seen linear systems in a course in differential equations, so-called predator-prey models. We're not going to go quite that far with our analysis today. We're just going to be looking at basic equations. So what is a linear system for the purpose of this video? Well, I'm glad you asked. Let me show you some examples. You might have two equations and two unknowns. The powers of x and y are all power 1, and the letters in front of them, the coefficients, are all constants. So two equations, two unknowns, two equations, two unknowns. You can ramp that up and have two equations and three unknowns. So here you'd want to be solving for x, y, and z, or three equations and three unknowns. It can go on and on and on. In this video, we're just going to solve two equations and two unknowns. Okay, and in other videos, we'll do the two equations and three unknowns. Okay, they'll be the subject of other videos. All right, so one set of principles that can keep you in good stead for all approaches to linear systems is the following advice. The idea is to convert the linear system into a simplified form that reveals the nature of solutions. And in particular, you can do three kinds of operations if you like. You can interchange equations, you can multiply an equation by a non-zero number, and you can add or subtract, if you like, a multiple of one equation to or from another equation. So let me just give you an example here. These are the kind of examples we're going to look at today. Two equations, two unknowns, right? Let's just look at, say, the first equation. All right. Now, interchange equations. You have that's the first equation, that's the second equation. You can switch the order around. This could be the first equation and that could be the second equation just by writing this up here. It hasn't changed the problem at all and it hasn't changed the nature of the solutions. You can multiply an equation by a non-zero number. So for example, down here, you could multiply that second equation by a half. It hasn't changed the structure of the solutions. And you can add a multiple of one equation to another equation. So you could take this equation and add it to this equation. And it still doesn't change the structure. Okay? So that's a little snapshot of what you can do to these linear systems to put them in simplified form. Okay? So let's keep going with this two equations, and two unknowns theme. What's going on there geometrically? Again, I'm glad you asked. All right, so geometrically, we are considering the graphs of two lines. For these two equations and two unknowns, that's what we're looking at. Now, two straight lines will either touch each other at one point only, and the point of intersection will be the unique solution, the one and only one solution to the linear system. You can have parallel lines that don't touch each other. In that case, there's no solution to your linear system. Well, the third case is that they're parallel and they're actually lying on top of each other to form identical lines. And again, you've got an infinite number of solutions to our linear system. Okay, so let me just give you some examples of that, and we can see how it works in practice. Okay, so let me share my Geogebra screen with you. Okay, now let's look at the line x plus 2y equals 4. And let's look at the line x minus 2y equals -2. Now you can see there that these two lines cross each other at one and only one point. So here x would be 1 and y would be 3 on 2. So that is a unique solution. That's the first case. Okay. What about if we had x plus 2y equals 4 and x plus 2y equals 1? Aha, you can see there that these two lines are parallel lines. They don't lie on top of each other, so they don't intersect in any way. So there's no solution. The lines never touch each other. And what about if I put in something like this? I'm just going to type in another equation. 2x plus 4y equals 8. What happens there? Oh, well, you can see, if I blow that up a little bit, let me make the thickness a bit bigger, that actually the two lines are on top of each other. So that would have that's the third case, an infinite number of solutions. Okay? Okay, you can see it's actually simplified itself to the first equation there. Okay. So why have I spent a lot of time doing that? Well, actually, they're all the lines that are involved with the three examples we're going to look at. Okay, so the first set had one and only one solution where the lines crossed. The second set had parallel lines that didn't touch. And the third set actually were one and the same line, identical lines. Let's actually go through and do the algebra of that now. If I can find it. Just give me a second. Aha. Here we go. Discuss the following linear systems. Okay, so let's start with this one here. And let's label them 1 and 2. Okay, so what we're going to do is, if I see I can add the second equation to the first equation, then I can eliminate one of the variables y. Okay, so let's do that. So equation 1 plus equation 2 gives the following. Well, it'll be x plus x, which will give you 2x. It'll be 2y minus 2y, which will give you 0, and 4 minus 2, which will give you 4 minus 2, which is 2. All right, so now we can just divide the 2 out and we'll get x equals 1. Now back substitute, so take that x equals 1 and put it into either 2 or 1. I'm going to choose 2. So you back sub x equals 1 in equation 2 to get the following. You're going to get oh, actually, let's put it into 1. It doesn't matter which one you do. I'll put it into 1 to get 1 plus 2y equals 4. So you take the 1 to the other side, you'll get 3 over there, and then divide through 3 on 2. Okay, so this then is the first situation that I showed you in Geogebra, where these two curves cut each other at one and only one point. So the unique solution is x equals 1, y equals 3 on 2. Okay, great. So that's the first solution. What about the second set of equations? Let's go through and solve those. Now we know from the Geogebra demonstration they're going to be parallel lines, but actually let's algebraically have a look at it. All right, so let's look at this equation now, this linear system, and let's label it, I don't know, 3 and 4. Okay, and with this one, what we can do is say take the equation 4 away from equation 3. That will eliminate all the x's and all the y's. Okay, so let's do that. So equation 4 minus equation 3, what are we going to get? Well, this is identical, so this thing is just going to go to 0 on the left-hand side. On the right-hand side, we're going to have, well, actually, let's, okay, we're going to have -3. Okay, you could have taken 4 away from 3 as well. You would have got a +3 there. Now, obviously, this doesn't make sense. You got 0 equals -3. So we come up to some nonsensical thing. So what it means is there can never be a solution to this linear system here. So we have no solution. And if you be parallel lines that don't touch. All right. And for the last one, so that has no solution. And for the last one, let's have a look at that one. So we're looking at that system there. We can label it 5 and 6. And well, you can see that if I say divide equation 6 by 2 or multiply it by a half, I'll get the same equation as equation 5. Another way of doing that would be, say, to take half of equation 6 away from equation 5. And what you'll get is 0 on the left-hand side and 0 on the right-hand side. So let's do it that way, okay? Yeah. So equation, I can do it the other way. Equation 6 minus 2 times equation 5. Okay, let me move that up. That's going to give you 2x plus 4y on the left-hand side. That's the same. You're going to get 8. 0 equals 0. Okay? So this is an infinite number of solutions. And they are identical lines. Okay. So no solution, infinite number of solutions. Okay, so it took me a little while, and I did a couple of those in a roundabout way, but you can see there's an example there that illustrates each of the three cases. They either cross, they're either parallel, or they're the actual same line. Okay. Now, in the next video, I'll show you how to solve 2 equations and 3 unknowns. That's a little trickier. If you have any questions, any comments, you can put them in the comments section. Probably a good question would be, so what's the solution to the last one then? So it's got an infinite number of solutions, but what are they? Well, what you can do here is, okay, you've got, so let's just worry about this last one now. Okay, what you can do here is say, take the fifth equation, let say, I don't know, introduce what's called a parameter, lambda. Sometimes people use mu here. And then all you do is you rearrange to make x the subject. So x equals 4 minus 2y. So let's replace y with lambda. Okay, so you've got what y in terms of lambda, you've got x in terms of lambda. What you can do now is write these things in a vector form. Okay, so you write x, y as a vector, so replace x with 4 minus 2y, 2 lambda, and y equals lambda. And then what you can do is break this up and write it in a vector form. So you bring the constant vector at the front, you bring the lambda at the front, and here lambda is the parameter. So here's the set of real numbers. Okay, so what is the solution? The solution to this system is basically the lines themselves. This can be written in vector form in the following way. So this line that passes through the vector or the point associated with this vector. Let's say it's the point big A, and is parallel to this vector. Parallel. Okay. So if you really wanted to go to finish off that last question, that's how you do it. Now, if you're not sure about where this comes from, I have lots of videos on the parametric vector form for a line and stuff like that. Okay, so what do you think? Any comments, any questions? Put them in the comment section. I'll do a more complicated example in my next video. Hope you can join me for that. See you later, everyone. Bye.